So the next one. We have two more vectors given, which are called C1 and C2. Again, these are Cartesian coordinates, if nothing else is written, with the values of -1, 2, 0, 2, 1, 3. And now the question is, what is the geometric, or which is the geometric representation of this vector space? This is, you could say, behind this is the idea that two vectors in three-dimensional vector space span a so-called plane if they are linearly independent. And with two vectors, it's easy to see, are they linearly independent, yes or no? And we see they are, because they obviously are not multiples of each other. So they show in different directions. They span a plane, and in the end, the question is, what is the set of all linear combinations of these two vectors? It's this plane, and this plane should be given in scalar form, just as a little training. Find a scalar equation which defines this vector space. This is like in school called analytical geometry, you could say, and we'll do it. And then finally, we will ask about a certain, introducing another vector, then finding out whether something changes or not. Okay, so with the third, it starts this way. I say that C1 and C2 are obviously linearly independent, so I don't have to, I think I don't have to comment this, I just did. They span a 2D plane. C1, C2 is a subspace. Actually, this is just now the symbolic notation for a two-dimensional subspace embedded in this three-dimensional vector space V over R3. You know what I mean? You could also say a two-dimensional planar manifold. This is the technical term, embedded into our whole R3 vector space. But now, rather simply, we can remember from school that since these two vectors are obviously contained in their own plane, which they span, they are also well fitted to be used as direction vectors, as vectors along this plane. And you know what you can do? This is quite easy. This time you take the cross product, the vector product of these two, which I call n, like normal. And this is the easiest way to construct a vector which is a normal vector. You know why? Because the vector product, cross product, it should be called vector product officially, always gives you a vector which is perpendicular as well to C1 in this case as to C2. You know this, right? So the result is perpendicular to both of these vectors. So now what I'm doing is I take them -1, 2, 0, and 2, 1, 3, and I build the cross product, the vector product. Why? How do you do this? Just to remember, there are different little rules to remember how to do it. My one is like a cycle diagram, if you know what I mean. In my mind, I go around and round, 1, 2, 3, always in a circle like this. And this is all I need to remember how the cross product is to be taken. I'll show you, okay? I go into the first row. The first row, so I'm here. And then I take second times third. That's what I do. Second times third means the second component or coordinate of this vector and the third component of this one. 2 times 3, which is 6. But then I must remember minus vice versa. Okay, so second times third minus third times second. That's my circle diagram. So I had 2 times 3 and then minus third times second is 0 times 1. But since 0 times 1 is 0, I don't have to do anything. It stays with 2 times 3 equals 6. That's my first row result. The second row goes, I'm here, then I say third times first. Okay, so I go to the first component of this vector times the third of this one, which is now -1 times 3 is -3, and then minus vice versa, minus means minus this one times this one. Again, a 0 is here, so I don't get a contribution, but I have my -1 times 3, which is -3. Oh, why is it? Sorry. You see, I made a mistake. I'm in the second row. I have to take the third, you see, my mistake. Third times first. Third component times first component. So I had to say 0 times 2 first, which is 0, and then minus vice versa, minus -1 times 3, which is +3. I'm sorry, was the wrong order. And if you have your different way of remembering, just use it, or even this cross method, you know this? You can use the cross as a tool and say, I put my cross here for the first row, this times this, but then you would have to remember in which order. So anyway, I don't think this is better or worse. Okay, I show you again what I'm doing, although I made a little mistake right now. So I go to the third row. I'm here in my diagram, and I say first times second. First of this times second of this. So now it must be right. -1 times 1 is -1. Minus vice versa means -2 times 2. -1 minus 4 is -5. So now it's correct. So it's quite easy, actually, to remember this way. So that's it. And yet now we have to make, to remember that this is a valid normal vector to the plane we want to describe. And you all know that the so-called scalar form of a planar equation, the equation of a plane inside a three-dimensional vector space. By the way, it's in this case, it's a plane which contains the origin. That's because we are doing linear algebra, so there's nothing moved to outside of the origin. The origin must always belong to such a plane or such a subvector space. That's another thing. And of course, you know what I'm doing? What I'm doing now is to say that n, a normal vector n, scalar product with any location vector x lying in this plane must be equal to always the same constant value. In this case, the constant is 0 because the origin is contained in the plane. You know all this. Why is this? It's because the component of each valid vector, the plane vector x. So one of the location vectors which lie on this plane, its component in direction of the normal vector must always be the same. This is what you see if you make a little graphical sketch. So that's what makes the normal vector so special. It describes the orientation of a plane perfectly. This means what we would have to write here is then our normal vector with the components 6, 3, -5, and then take the scalar product with our vector x1, x2, x3. And this is what I do. And you know that the scalar product works like multiplying and then summing up, yeah? Like 6x1 plus 3x2 and so on. And that's what I've done here. You can recognize the normal vector here with its components 6, 3, -5. And then, so you could say this is a scalar product which has already been performed. And then the result must be equal to 0 because the origin is inside. So that was like a little away from classical linear algebra now, or vector algebra. But I wanted to just to use the cross product once, that's the scalar product and whatever we have. And the remaining exercises are some more special, again, about this topic of vector multiplication. So the fourth one is quite easy because look at the text here. It says that given one more vector, C3, with components 3, -1, 3, show that these three vectors now are linearly dependent. That's one thing. And then the question is now C1, C2, this set of linear equations, or this subspace, let's call it subspace, is this equal to C1, C2, C3 subspace? And now what you should understand is being, for three vectors to be linearly dependent, it means that they all lie in the same plane. Okay, that's exactly what it means. It means that you can express one of these vectors, arbitrarily one of them, by a linear combination of the others. So you could, for example, you could also express C3 as a linear combination of C1 and C2. That's what it means. And since any linear combination of C1 and C2 is what's contained here, it's clear that it doesn't help any to bring C3 into play. If C3 also lies in the same plane as C1 and C2 do, which they span also, so it means that these three vectors span exactly the same plane as these other two. It's not possible to reach, to leave this plane by introducing vector C3, since it's linearly dependent of the others two, from the other two. That's what it's all about. And so without any clumsy calculation, it's quite obvious that the answer is yes, these two subspaces and vector spaces are identical. Actually, it should be shown that they are linearly dependent, and this is what I missed. Okay, so this is a very short answer. Yes, since it's a fact that the third one is a linear combination of the other two, if they are linearly dependent. But you see, I had run out of space here, and then I forgot to show that they are linearly dependent. I hope we can just leave it away for now.